Square ABCD, shown here, has side length of 6 units. Points P and Q are located on sides AD and BC respectively, with AP equals to BQ equals to 1. Triangles ACP and BDQ overlap in the square to form the shaded quadrilateral. This one. What is the area of the shaded quadrilateral? Express your answer as a common fraction. Now, before we go into details and try to solve this problem, first we need to know certain things we're going to use in the solution. And that is triangle similarity. As a general rule, there are a lot of problems, especially in Olympiad settings, where the people who make these problems want you to know triangle similarity and use it. So it's a good thing to know what it is and how to use it. So let's go first review that. So if you have two triangles, ABC and A prime, B prime, C prime, we're going to say that these two triangles are similar if all three angles of one triangle are congruent with three angles of another triangle, obviously respective angles. So angle A is congruent to angle A prime, angle B is congruent to angle B prime, angle C and angle C prime are congruent. And in addition, we're going to have that ratio of respective sides are also proportional with the same proportionality constant. What I mean by that, if you take the side AB, for example, and divide by side A prime, B prime, that ratio is going to be the same as the ratio of the side BC to B prime, C prime, and ratio of the side AC to the side A prime, C prime. In addition to this, in addition to proportionality of the sides, other things about these triangles are also going to be proportional with the same proportionality constant. For example, angle bisectors, side bisectors, altitudes, they're also going to be proportional with the same proportionality constant. It's like as if you take a picture of one of the triangle and then you basically zoom in or zoom out, basically enlarge it without distortion or reduce the side without distortion. Those kind of operations will give you similar objects. In this case, it doesn't really matter whether it's triangle or not. But for triangles, we have such nice properties, as we'll see. So in our case, we're interested in altitude. So let's look at the altitude BD and B prime, D prime. Just to remind you what altitude is the line or a segment that starts from one vertex, in this case vertex B and B prime, and is perpendicular to the opposite side, which means that BD become perpendicular at 90 degrees to AC, B prime, D prime is perpendicular to A prime, C prime. Okay? And what happens if you know that these two triangles are similar, BD over BD, B prime, D prime is going to be the same as the ratio of the sides. Okay? So there are a lot of nice properties if you know that the triangles are similar. Now the question is, how do we find that triangles are similar? Obviously, if you check all these properties, all the black properties, that will give you similar triangles, but obviously it's too much to check. We need to have some smaller set of things we can check quickly to declare that two triangles are similar. And if you study geometry, you'll know there are three criteria of similarity. We're going to talk about one criteria today. That's most commonly used criteria, and that criteria um, of two angles. So if you can show that two angles of one triangle are congruent to two angles of the other triangle, respective angles. So for example, if you show that angle A and angle A prime are congruent and angle B and angle B prime are congruent, that's sufficient to claim that the triangles are similar, okay? And all other properties are going to fall in from that, okay? And there are two main kind of arrangement that you see in many geometrical problems where you see this kind of triangles, similar triangles. The first arrangement we're going to look at is when we have an angle, I call it angle A, and we have two parallel lines intersecting this angle, BC and B prime, C prime. In this case, we get two triangles, the small triangle ABC and the bigger triangle AB prime, C prime. Those two triangles are going to be similar by two angles. First angle is angle A. It's shared by these two triangles. So angle A is obviously congruent to itself. And now that we can choose either BB prime or CC prime, let's choose CC prime. Those two angles are congruent because they are corresponding angles for parallel lines, BC and B prime, C prime. And that makes those two triangles similar. The other arrangement is when we have two lines intersecting. In this case, they're intersecting point A. And again, we have two parallel lines intersecting those two blue lines. And in this case, again, a triangle ABC and triangle AB prime, C prime are going to be similar because, well, by two angles. Because first of all, angles, those two angles A's are congruent because they're vertical. Vertical angles are always congruent. And then again, we can pick up either C or B. Let's pick up C and C prime. Those are congruent because they are alternate interior angles for two parallel lines. All right. So, and those are typical arrangements which we should always look for when we are trying to solve a geometric problem. All right, let's go back to our problem. I zoom up our square, and I also name this gray quadrilateral as KGLH, okay? Now, what we can do here, and what we're going to do, we're going to split this square in half vertically, like this. And what we find now, what's on the right, is a mirror image of what's on the left. Those are two congruent parts, actually. And what happened here, we split this quadrilateral KGLH into two parts, which are into two triangles, actually, which are congruent triangles. So GLH is congruent to GKH. That means that if you find the area of one of them, they're going to have the same area, and together, two of them are going to give us the area of the quadrilateral. That's also a trick that's worth knowing, that, you know, if you have some shape and somebody asks you to calculate the area, you don't know how to calculate the area of the shape, just split it in triangles. And we know how to deal with triangles. Now, how do we calculate the area of GLH, for example? Well, the area of the triangle is the base times height. Well, we can use this GH as our base, and now we need a height in altitude going from the vertex L onto the line GH. We can get that line by connecting K and L points. We're going to get a line that is parallel to AB and CD sides of the square. All right. And let's call the intersection of those red lines point O. In this case, LO is going to be the height, altitude of the triangle GLH, okay? So the area of this triangle GLH is half of GH times LO. And the area of the quadrilateral is 2 of areas of those triangles. And that's going to be simply just GH times LO. Okay? And now we need to find GH and LO. Let's start with GH. And now what we need to look at is this angle, PCA. Okay? That angle actually is split across by 2 parallel lines. One of them is that red line, the other is this side of the square AD. Okay? So it's going to look like this. And we already have seen this arrangement. In this case, this small triangle GCH and the big triangle PCA are congruent by 2 angles. And what does it mean? It means that the sides are proportional, the altitudes are proportional. So what we need in this case is the ratio of the sides, PA and GH, and the ratio of the altitudes, which are EC and DC, okay? We know the triangles are similar, and we know this, we have this ratio, okay? But we know what CE to CD is. CE is half CD, C is 3, CD is 6, so the ratio is half. Also, we know that PA is 1. It's given to you. And that gives us GH, which is 1/2. All right, we found GH. Now let's find LO. Let's find the height. Okay. To do that, if you stare at this picture you have, you will find that if you look at this line, DQ, and also if you look at the other line, AC, those 2 lines intersect at point L, okay? And those 2 lines actually are crossed by 2 parallel lines, a line AD and line BC, sides of the square, okay? And we say, this is our arrangement like this. And it makes the triangle on the left and triangle on the right similar. Okay, this DLA and QLC are similar by 2 angles. So it means again, so the sides and altitudes have to be proportional. And in this case, the side I'm interested in, or sides I'm interested in, is side AD and side CQ. And the altitude I'm interested in is LM and LN, okay? And also, I immediately said that this AD to QC is 6,5 because we know AD is 6, it's the side of the square, QC is a part of the square, and that is 5, okay? It means that the altitude ML, ratio of ML to LN, is 6/5, okay? But the next thing to note is actually ML and LN are related because together ML plus LN give us this side, horizontal side of the square, which is 6, okay? And now what we can do, we can replace LN with ML as 6 minus ML and get an equation we can solve. One equation, one unknown. We solve it both 2 ways. One way is to see that this is a proportion. Another way to just simply look at this as the equation and I say, well, I'm going to multiply both parts of this equation by the product of these 2 denominators. So we're going to multiply both parts by 5 and by 6 minus ML. If we do, we get expression like this. Open the parentheses, combine MLs. You get 11 ml equals 36. Now we divide both parts of this equation by 11, and we get our ml as 36/11. Okay? Now, that's good, but I'm not interested in ML. I'm interested in LO. And to understand what LO is really, if you look at whole ML, we can split in two parts. One is MO, and now there's LO. And MO is a half of the side of the square. So MO is going to be 3, and the rest of it is LO. Okay? This is saying ML equals MO and LO. We know what MO is. We take LO as ML minus MO, and we get 3/11. Okay? And now we're done. Basically, we know GH is half, we know LO is 3/11. We multiply them together and get 3/22.